Welcome back. Now when we understand how to use a simple clustering, let us understand if we can also use neural networks, since we put so much efforts into learning them, to do some unsupervised things with charge stability diagrams. So before we saw some different flavors of this task. We have a charge stability diagrams and we just want to predict whether they are in a single dot or a double dot regime or what kind of transitions we are seeing on a measured patch. So everything was a feed-forward labeled task. The question is if we could be able to work without labels altogether. The answer is that you can. And generally, how it works is that you can build some kind of generative model. In this case, the generative model we are going to use is called autoencoder. And what it does is that you can basically take the architecture that you had, as in you go from your input to some kind of output, but then you continue and you try to reconstruct your output again. So what this type of neural network would be doing is nothing too sophisticated. It just takes your charge stability diagrams on the input, compresses them to some smaller representation, and then it tries to reconstruct them into the output. So the training criterion for weights and biases in this kind of neural network would just be input minus output, square that, minimize. So it's a very similar type of loss functions we were working with, but now we are comparing just input to the output of neural network and not with some human or machine assigned label. Why is this interesting or relevant at all is the question whether a network maybe learn something useful or generalized low-dimensional representation of your data when it compresses to this sort of smaller representation. The way to think about it is that you could have like this a customized compression algorithm for your images. In a world where JPEG and many other compression techniques already exist, this would be really silly and impractical to do, because why would you train a neural network to sort of compress your data if there are really great and super efficient data agnostic compression algorithms out there? Where it becomes interesting is from the more interpretation point of view, because if you can get your neural network here in a compressed representation to extract something meaningful about your data set that possibly you can interpret and use for a data analysis, that would be quite nice and useful, right? So this is really the spirit of the autoencoder, where the forward network takes your input and compresses it to some kind of lower dimensional latent space. This is called encoder. And then feeds it to the decoder, which is pretty much the inverse of what you did here, but you just go from a lower input to the much bigger output. How this works coding-wise is very similar to what we learned, especially this encoder. This is just your normal feed-forward network, can be convolutional or dense, doesn't matter. Here, when you are decoding, you sort of need to do a transpose version of your layers. Vinny is going to show you exactly how. So there is just a little bit more coding syntax going into it. But if you keep an eye on your input-output dimensions, it's actually not hard at all. So we are just like slightly generalizing the neural network architectures that we have already learned. Now, the question is why this would be helpful. So in your reading submodule just before this lecture, you read more about PCA and you also saw examples of other nonlinear clustering techniques. Sometimes I have a data that I just have a good feeling what should work and I use that specific clustering techniques. But sometimes I don't know what to do at all, and no quick choices of my clustering or kernels is giving me a good result. So that means that I have to try a ton of different things and adjust a lot of hyperparameters to sort of make a clustering to give me information that I want. It can be in a situation where you don't know what to do at all, that if you play with the dimension of the latent space, the neural network sort of learns for you what's the best clustering method or a kernel that you should use to map your problem into some low dimensional data space that is a good representation of your problem. So this is the reason why people were very interested in this, and in relation to interpretation of physics, there have been some really nice results already using this kind of general philosophy. Now the question is if the same thing applies on a quantum dot data. So when you build a neural network that follows this autoencoder structure and just unleash it on your data set of a different charge stability diagrams that we created for you, you are going to get a plot like this, where one color corresponds to a single dot diagrams and the other color to a double dot diagrams. So the only thing you need to figure out is where is the transition between the two regimes. And if you know that, then your latent space can be your classifier. Another fun thing to notice here, we plotted this in 2 dimensions for the sake of argument, but you actually don't need the second dimension. Everything gets beautifully compressed just along one line, and somewhere in the middle of the line you have a crossover between going from double dot to a single dot, and we achieve this just by running the data through the autoencoder without any specific labeling or anything like that. So that's pretty cool, right? So you can indeed plot your charge stability diagrams together with the dot that tells you where in the cluster your charge stability diagram lives. And you will quickly see that the single dot charge stability diagrams are blue and the double dot charge stability diagrams are purple. So basically we obtained again this kind of classification with no labels, just looking at the plot of the latent space. So now let's look what you are going to do in your coding exercise. So first, Winnie is going to walk you through of how to cluster charge stability diagrams with the PCA, and you are going to recreate a plot that is very similar to this one, and you will learn how to identify your charge stability diagram within your cluster. As we discussed before, this is not an ultimate solution, but it's pretty interesting that even this like a super simple linear transformation lets you see a separated blob, at least for one type of charge stability diagram. If you want, you are super welcome to experiment with the different kernels and making it nonlinear. Winnie has some interesting exercises ready for you there. In the second part, you are going to train autoencoder by slightly generalizing the neural networks you had in your hands-on before, and you are going to plot exactly this type of plot, and then as an exercise you will have to find what is the cutoff between purple and blue here in your latent space, and when you find it, you will have a latent space based classifier of your charge stability diagram without any labels included.